Hi there. So in this video, we are going to look at sketching the graph of the derivative function. So given the graph of a function, analyzing it, and then from there, kind of putting the pieces together to make a sketch of what its derivative, the graph of its derivative function might look like. So this is without knowing what the equation of the graph is and like finding the derivative and from there sketching from an equation. This is analyzing a given graph in order to sketch the derivatives graph. And we're also going to look at when we're given the derivative graph, what kind of characteristics about the original function we could identify. So what we currently have in our derivatives toolbox, and we're going to continue to add tools to our derivatives toolbox in order to identify different aspects, characteristics of functions that will be helpful. But what we currently know is what a tangent line is, and we can kind of eyeball the slope of a tangent line at a point on a curve. In other words, negative sloping tangent lines, we know that correspond to the derivative being negative, right? Less than zero. Positive sloping tangent lines would correspond to the derivative being positive at a point and therefore greater than zero. And then horizontal tangent lines have a slope of zero, therefore the derivative would be equal to zero. So remember, the derivative is a function itself with its own graph. You can pull out information about its graph from analyzing the graph of the original function. So here I've given us the graph of f of x, and we want to figure out what f prime would look like a rough sketch of what f prime would look like, kind of from the information that I've listed above. So I'm going to start by looking for where it appears there are horizontal tangent lines. So where f prime would be equal to 0, because those are going to be x-intercepts on the graph of f prime. So it looks like at x equals to -3, there's a horizontal tangent line, and x equals to -1. And this is just eyeballing the graph, right? I don't know the actual equation. It also looks like the graph levels off at x equals to 2. And that we could say there's a horizontal tangent line there. And then also at x equals to 4. So the location of the horizontal tangent line will correspond to x-intercepts on the graph of f prime. So I'll graph those points. So -3, 0, -1, 0, 2, 0, and 4, 0. And then to determine what happens to the left and right of each of those x-intercepts, I can read the graph from left to right. And next I can think, okay, so to the left of -3, if I were to draw a tangent line to a point, it would be negative sloping, right? All the points to the left of -3. So from -infinity up to -3, all of those points on the graph of f have negative sloping tangent lines, meaning f prime would be negative. Right, so f prime would be values below the x-axis. So from -infinity to -3. And they also look like pretty steep sloping tangent lines. So I think that it would get, the values of the function would be small pretty quickly to the left of -3. And then to the right of -3, so between -3 and -1, it looks like if we were to draw a tangent line to different points, right, we would have a positive sloping tangent line, meaning the graph would go above the x-axis. So it would come up. And then when we want to look at between -1 and 2, and it looks like there would be negative sloping tangent lines between -1 and 2. So the graph would dip below the x-axis again. And then between +2 and 4, still negative sloping tangent lines. So the graph isn't going to cross the x-axis at 2. It's going to bounce off of the x-axis. And then to the right of 4, so from 4 to infinity, it looks like there would be positive sloping tangent lines again. So the graph would cross and be positive. So something like that would be a sketch of f prime. Now we could kind of really like try and estimate what the slopes of the tangent lines are at different points to make it more accurate, but this is just kind of a rough sketch of what the derivative graph would look like. Okay, so let's try, this is kind of a different looking graph. This one is not a smooth continuous curve. Like the previous example, the given graph of f of x probably represented a polynomial function, right? Which was a smooth continuous curve and therefore differentiable at every point in its domain. But this graph is not. There's some sharp corners on this graph where like the slope of the points of the tangent lines change kind of at a sharp corner. That first sharp corner looks like it occurs at -3. And then at x equals to 1, x equals to 3. And that's it. Those look like those are the sharp corners. So what I want to look at is from -infinity to -3, what does it look like the slopes? We could think of this graph as kind of being different line segments. And it looks like to the left of -3, so from -infinity to -3, it looks like the slope of each point would be -1. That's just examining the slope of this line. So that means that f prime from -infinity to -3, f prime would be equal to -1. Right? Up to -3 would be equal to -1. Or g prime, sorry, this is g prime. -3, x equals to -3 doesn't look like it's differentiable. There's a sharp corner there where kind of like an absolute value function, not as sharp as at x equals to 0 for the absolute value function, but the slopes just drastically change at x equals to -3, creating that sharp corner. Here, let me use a different color here. Between -3 and 1, it looks like the slope at all the points between -3 and 1 would be -3/2. Right? Down 3, right 2. So -3/2, which is -1.5, between -3 and 1. That doesn't look like -1.5. Let's try that again. Okay. And then between 1 and 3, well, the slope, that's a horizontal line, and the slope of a horizontal line would be 0. So between 1 and 3, y equals to 0 is what g prime would look like. And then from 3 to positive infinity, it looks like the slope would be 2. From 3 to positive infinity. Okay, so this is a sketch of g prime. We're going to get better as we continue to add, become more familiar with derivatives and what they can tell us about a function. we're going to get better at determining what the graph of a function and its derivative look like. But for now, just estimating slopes of tangent lines, and what those corresponding values to the derivative would be is what we're using here. Okay, sample multiple choice question. So given the graph of f of x, which of the following would be the graph of f prime? So what I like to look for first is horizontal tangent lines, because those are going to correspond to x-intercepts for the derivative. And it looks like there's a horizontal tangent line at -2 as well as +2. And it looks like there are two graphs. So A and D both have x-intercepts at -2 and 2. So it's either one of those, and we can throw out B, C, and E. So then we look to the left of -2, and we would have positive sloping tangent lines to the left of -2, meaning f prime would be positive. Well, that's only the graph in A, right? F prime is positive to the left of -2. And then between, if we want to finish analyzing this, between -2 and 2, negative sloping tangent lines, and we can see the graph would be negative on the graph of A. And then positive sloping tangent lines again means the graph switches back to being above the x-axis. Okay, so A would be the best graph of f prime, given this graph of f of x. Just some more examples to reference. So each of these, like f and f prime, and just to separate them, and then f and f prime, f and f prime. Let me know if you have questions on these ones. Okay, a little bit different question. Below is the graph of h prime, and you are given h of 0 is equal to 2. So h of 0 equal to 2, that represents the point 0, 2 on the graph of h. So I can go ahead and graph that point. That's helpful. Sketch the graph of h of x. So it looks like from -infinity up to 1, the slope of h would be -1, right? Because that's a horizontal line at y equals to -1 on the graph of h prime. So it looks like the slope to the left of 1 would be -1. So to go off of the 1 point that we know, the graph would need to look like that. Now, whether h is defined, we haven't been given whether h is a continuous function. That would have been helpful information. We don't know whether h is actually defined at x equals to 1, but because we haven't been given that information, you can draw it as defined or you can draw it undefined. That's up to you. But what we do know is to the right of 1, so from 1 to infinity, the slopes of the tangent lines, slopes of the points on the graph of h would be +2. I'm going to draw h as being continuous, but like I said, you could do either. So it looks kind of like a funky absolute value. This would be our sketch of h of x. Okay, and then this is the graph of p prime. We're going to answer these questions. So what is the value of p prime of 0? That's just reading the graph. And p prime of 0, that corresponds to the point 0, 4. P prime of 0 is equal to 4. And p prime, all of those function values give us the slopes of the tangent lines at the corresponding x values on the graph of P. So what that statement tells us, what P prime of 0 tells us, is that P of x has a slope of 4 at x equals to 0. Or you could say something like the slope of the tangent line on the graph of P of x is 4 at x equals to 0, something of that sort. But the slope of the tangent line corresponds to the slope of the graph. Okay, B, using the graph of P prime, how can you determine when the graph of P of x is going up? What I mean by that is, where's the graph increasing? So where, if you were walking along the graph from left to right, like you read a book, where would you feel like you're walking uphill? And that would be from negative infinity to 0. Yeah, negative infinity to 0. You would feel like oops, nope, I messed up on that. Sorry, brain fart. Okay, so using the graph of P prime, so on the graph of P of x, you would feel like you're walking uphill. For the graph of P of x to feel like you're walking uphill and being increasing, P prime would have to be positive because the slopes of the tangent lines would have to be positive. So we can say that P of x is increasing on the interval between negative 2 and 2. That's where P prime is positive, between negative 2 and 2. So P of x is increasing on the interval between negative 2 and 2, which is where P prime of x is greater than 0. P of x is decreasing on 2 intervals. So it's decreasing on the intervals from negative infinity to negative 2 and 2 to infinity, which is where P prime is less than 0, where there would be negative sloping tangent lines on the graph of P of x. So the graph of P prime crossed the x-axis at x equals to negative 2 and x equals to 2. Describe the behavior of the graph of P of x at these points. So P of x would have horizontal tangent lines at x equals to negative 2 and x equals to 2, which is where P prime is equal to 0. They are also going to be points where P of x changes from decreasing to increasing, increasing to decreasing, right? Because P prime changes signs, SIGN, at those points as well. So we can say P of x has horizontal tangent lines at x equals to negative 2 and x equals to positive 2, which is where P prime equals to 0. They are also points where P of x changes from decreasing to increasing and increasing to decreasing. Now we don't know the y values for those points on P of X, so it would be difficult. You could come up with a sketch of a graph that could fit this, but like your friend could sketch a different graph that would kind of fit these conditions at this point for the information that you are able to pull out from this graph.